What if the most destructive objects in the universe are also the key to understanding reality itself? Black holes aren't just cosmic vacuum cleaners swallowing everything. They're extreme gravity wells where space and time warp beyond recognition. Forget everything you thought you knew. In this video, we'll demystify the mind-bending science behind black holes, breaking down event horizons, spaghettification, and why these cosmic monsters aren't just theoretical. Get ready to finally understand the universe's ultimate mystery. Black holes are regions in spacetime where gravity is so strong that nothing, including light and other electromagnetic waves, has enough energy to escape once it has entered past a certain boundary. They form from the remnants of massive stars that collapse under their own gravity at the end of their life cycle. This gravitational collapse compresses an enormous amount of matter into an incredibly small volume, creating a region of extreme density. The boundary surrounding a black hole beyond which matter and light cannot escape is called the event horizon. This is not a physical surface, but a theoretical point of no return. Once anything crosses the event horizon, it is irrevocably drawn towards the center due to the overwhelming gravitational force, unable to send any information back out. At the very center of a black hole, according to general relativity, lies a gravitational singularity. This is a point of infinite density and zero volume, where the laws of physics as we currently understand them are thought to break down. All the mass of the black hole is theoretically concentrated at this single, infinitely small point. The immense gravitational pull of a black hole results from a vast amount of mass being concentrated into an incredibly compact region of space. For example, a stellar mass black hole can contain several times the mass of our Sun, compressed into a sphere only tens of kilometers across. This extreme density generates a gravitational field far stronger than that of ordinary celestial bodies. Black holes dramatically warp the fabric of spacetime around them, a phenomenon predicted by Albert Einstein's theory of general relativity. This warping affects the paths of light and matter, causing them to curve inwards towards the black hole. The distortion of spacetime is so profound that time itself would appear to slow down for an observer approaching the event horizon, relative to a distant observer. There are primarily two main types of black holes known: stellar mass black holes and supermassive black holes. Stellar mass black holes typically have masses between 5 and 100 times that of our Sun and are formed from the collapse of massive stars. Supermassive black holes, by contrast, can contain millions to billions of solar masses and reside at the centers of most large galaxies. Directly observing black holes is impossible because they do not emit light, but their presence is inferred through their powerful gravitational effects on surrounding matter and light. Scientists detect them by observing the behavior of stars orbiting an unseen massive object, or by detecting the intense X-rays emitted from superheated gas in accretion disks. These disks form as matter spirals inwards towards the black hole, heating up to millions of degrees. Quantum mechanics suggests that black holes are not entirely black, but can slowly radiate energy away in the form of particles, a phenomenon known as Hawking radiation. This theoretical process, proposed by physicist Stephen Hawking, implies that black holes have a temperature and can gradually lose mass over extremely long periods. Eventually, over timescales far longer than the current age of the universe, a black hole could theoretically evaporate completely. As gas and dust from nearby stars or interstellar clouds are drawn into a black hole's gravitational field, they often form a rapidly spinning structure called an accretion disk. The material within this disk heats up to extreme temperatures due to friction and compression as it spirals inward. This superheated gas emits vast amounts of electromagnetic radiation, particularly in X-rays, which allows astronomers to indirectly detect and study black holes. Supermassive black holes are found at the centers of most large galaxies, including our own Milky Way galaxy, where Sagittarius A time is located. These colossal black holes can significantly influence the evolution of their host galaxies, affecting star formation rates and the distribution of gas and dust. Their powerful jets of plasma can also extend far into intergalactic space, impacting the surrounding cosmic environment. Thanks for watching. Please subscribe to our channel.